So let me start then. So thank you to give this talk. I will be talking about second law for active heat engines today. So this is a prototypical heat engine within stochastic thermodynamics. The difference here is that the heat engine is made of a single degree of freedom, right? And if you think about heat engines in thermodynamics, we think about systems that are macroscopic. So, they would have 10 to the power of 23 degrees of freedom. But in stochastic thermodynamics, we can do heat engines made of a few degrees of freedom. And I mean, this sort of cycle forms like a prototypical heat engine in stochastic thermodynamics that is a colloidal particle under the action of an harmonic potential. You start with a certain stiffness for the potential, then you change the stiffness. If you want to think in terms of macroscopic thermodynamics, you can see this as volume, right? So on the left, I have like a smaller volume, so the particle is more stick to the middle. And if I open up this parabola, then the particle has a higher probability to be farther away from the middle. So it's like increasing the volume. Then you change the temperature when you go from the red hot to the blue cold. And then you change back the stiffness of the parabola, and then you change back the temperature. Okay, so that's like a cycle similar to kind of a Stirling engine, but a heat engine that is made of a single degree of freedom. So it's the prototypical example of a heat engine in stochastic thermodynamics. And for such heat engine, you have the second law tells you that the efficiency of the heat engine must be bound by the Carnot efficiency. And works there have been a lot of works on heat engine in stochastic thermodynamics. This is the first experimental realization of such heat engine. But then in 2016, there was a paper that proposed the concept of an active heat engine. So it's the same sort of heat engine and a single colloidal particle in a parabola, in an harmonic potential. But now the bath is not a passive bath anymore. So this colloidal particle is not just in water, for instance, but it's in water filled with bacteria, okay? So these bacteria, they should be seen as part of the bath and not of your system. So the system is still just a single colloidal particle in the direction of an harmonic potential. And these bacteria made the bath active. Now, in this sort of interesting concept of active heat engine, there are two main observations in this paper. One is that the work that an active heat engine can do compared to its passive counterpart, which would be do the same experiment, but without the bacteria now, can be larger. So the work extracted for an active heat engine can be larger as compared to the passive counterpart. And the sort of a pseudo efficiency work divided by heat, it can be larger than the Carnot efficiency. So I'm calling this pseudo efficiency because when we talk about the heat here, this is the heat that we infer by measuring the position of the particle. Okay, so this is the heat associated with changes in position of this colloidal particle. This heat here, this QH, this heat taken from the hot reservoir, has nothing to do, or I mean, does not account for the energy dissipated by the bacteria. Okay, so there was this experiment in 2016, and there have been a few theoretical works on that. I mean, most of them would look at a single case study or a model inspired by this experiment, which again is a very interesting concept, the concept of a heat engine, but in an active reservoir. And here it's active because of the bacteria. Now, given this situation, I think the question that emerges is what's the appropriate statement of the second law for active heat engines, right? I mean, this statement of the second law should not have the energy dissipated by the bacteria because that's much larger than the work and the heat we are talking about. So if something is much larger, it will dominate such statement and will not provide a relevant bound, for example, on extracted work, right? So this appropriate statement of the second law should tell you what are the things that an active heat engine can do and what are the things that it cannot do. So again, the second law should not have the dissipated by bacteria, and it should account for this previous observation. One is that the active heat engine can extract more work than its passive counterpart, and that this pseudo efficiency, the work divided by the heat. Again, I'm calling pseudo efficiency because it doesn't account for this heat dissipated by this hidden dissipative degrees of freedom, which are the bacteria in the experiment. So it should account for these previous observations. And again, I don't want it to have this energy dissipated by the bacteria. Now, what will happen is that we will be able to answer this question. We were able to answer this question. And it turns out that the correct statement of the second law for an active heat engine will come from the excess entropy. Excess entropy is a quantity that is known in stochastic thermodynamics for quite some time. A main interest on this quantity comes from the fact that it fulfills a fluctuation theorem. So there is the standard entropy, which we can call total entropy. There is the excess entropy and the housekeeping entropy. So the total entropy is the excess entropy plus the housekeeping entropy, and all three of them fulfill fluctuation theorem. There is also something called non-adiabatic entropy and adiabatic. Those are terms coined by Massimiliano Esposito and Chris van den Broek. Excess entropy is associated with the non-adiabatic entropy. So from the proposals I'm talking about here, if you think about periodically driven system, you think about the average quantity, excess entropy and non-adiabatic entropy would be the same thing, okay? But this quantity was already known in stochastic thermodynamics. The point I want to make it here is that for active heat engines, this is the quantity that will give the right statement of a second or the appropriate statement of the second law for an active heat engine, which will have these properties that it will not contain the energy dissipated by the bacteria, and it will give you a good bound on the extracted work this heat engine can do, okay? Another important point is that when you work out this excess entropy, there will be an information theoretical term that will show up. So this energy dissipated by the bacteria will not show up, but some sort of information theoretic term associated with some probability distributions in the system will show up, okay? So basically, that's the story I'm going to tell you in this talk. For the next slides, I want to illustrate these points with a simple model. So the simple model is this model. It is similar in spirit to the experiment, but different. It's not the same model as the experiment, but it has the same physics, okay? And I mean, the good thing of this model is that you can solve it analytically. So this is a two-state model. It's also a heat engine. You have one state with energy 0, the other is some energy that's non-zero. So the first thing you do, you lift up the energy from E to E plus delta E. Then you change the temperature, then you change back the energy, and then you change the temperature, okay? Similar to the model, to the colloidal particle model. Now, for this case here, I can make it active by, for example, burning an ATP between the two states, okay? So this delta mu here would be the free energy of one ATP hydrolysis, right? So the green arrows, you could see it as dephosphorylation reaction. The red arrows could be the phosphorylation reaction. And physically, this could be like a molecule that has two conformation states, one with energy 0, the other with energy. And this molecule, when it goes to the up conformation state, will burn an ATP, okay? That's kind of what you could imagine. That's just a model you can imagine, which is, I would say, the simplest model for an active heat engine, okay? So if delta mu is equal to 0, this heat engine is going to be passive. I just will have the equilibrium distribution. So one state will have probability proportional to 1, the other will e to the power of minus beta E, beta being the inverse temperature. But if I turn on the delta mu, I will change this probability distribution, and I'm going to make this heat engine active, okay? Now, if you work out this model, which again, you can calculate everything exactly, it will present all the phenomenology of the model from the experiment, which would be a more complicated model. Or I mean, if you want to do a mathematical model of what's going on in the experiment with the colloidal particle, okay? But I mean, the first figure show that if I turn on the delta mu, so if you start with delta mu equals to 0, and if you increase the delta mu, you can increase the extracted work. So indeed, it is possible to find an active heat engine that will extract more work than its passive counterpart. And I mean, you can find a regime where the pseudo efficiency, that's what eta PS means. The pseudo efficiency is just the work divided by the hot heat. Again, this hot heat has nothing to do with the ATP consumption. It's just associated with energy change when you change from one state to another, okay? So the two observations in the main experiment, you can already have then with this very simple model. Coarse graining is missing here. So, when you do the experiment, there is the issue of coarse graining because there is all this bacteria that you can see. And if I was to only look at the position of the colloidal particle, I probably get some sort of no Markovian dynamics. I'm going to talk about coarse graining towards the end. But in the end, I mean, when you do coarse graining, none of what the physics I'm discussing here will not really going to change. Everything is going to remain the same. But it's a very important point because, if you imagine an experimental situation where I want to think about an active heat engine, probably this issue of coarse graining is going to be important. But the physics I'm discussing will not going to change once we do coarse graining, okay? So that's the simple model. Another result you can do for the simple model, you can calculate everything. Now, the second law in red is what I would call the standard second law of thermodynamics. That comes from the total entropy. Whenever you see a quantity here, this is the average entropy per period, okay? So this is not a rate, this is the total entropy integrated over one period of the engine. So if I calculate the standard second law, I get the second law in red, and the good one is the one for the excess entropy. I will get this one in blue, okay? This figure here is to make this idea that I'm talking about, that the energy dissipated by the bacteria is not a good quantity to have in your second law. Why is it not a good quantity? Because it has a very different scaling with a relevant physical parameter, which is the period of the engine tau. Okay, so if I look at the period of the engine tau, in black here, I have this term delta S active. For the case of the three-state model, that's just the amount of ATP you burn. And of course, I mean, if I keep increasing the period tau, the amount of ATP I burn just will increase linearly with tau, okay? But if I think about quantities like the work extracted per period, that thing is going to saturate, right? Because, you know, the maximum work I can extract is something like delta E, right, in a whole period. So I cannot extract more than delta E. If I keep increasing my tau, my work saturates, my heat saturates, but the heat dissipated in terms of, or the entropy associated with burning ATP is going to increase linearly with tau. So, you know, the second law in red is not a good second law. It's not a good statement of the second law for an active heat engine. That's just to make it more precise. Again, you can perform this calculation exactly with the three-state model. And the good second law is the one in blue. So the way the second law is going to look like is that when you write excess entropy, there will be the informational term, there will be the hot heat, and there will be the work. This informational term, I'm going to try to explain it as next slide. So what I want to do in the next 3 slides, 4 actually, is to give you an idea of how these things looks in general. So this is a very general theory. It's not only applied to the particular experiment. And I want to show you how these things look like in the next 3 or 4 slides. 4 slides. Okay, so, you know, the way we would work this out is you think about the master equation. So you would have transition rates which are periodic in time. They're periodic in time because we are looking at a periodic heat engine, right? So I'm changing temperature periodically in time, and I'm also changing the energy landscape periodically in time. So basically, one thing you want to do with this master equation is to solve the long time limit solution. You can call this a periodic steady state if you want. And, you know, you can calculate this probability pi for a given model, either numerically or exactly. Now, there is one other probability that is very important in this discussion, which is the PIS of T. So that's the stationary probability the system would have if I was to freeze my rates at a particular time T. So if you think about the 4 steps in the heat engine, let's say I fix my temperature, I fix my energy landscape, and I let the system evolve to a stationary state, that is this PIS of T. So one is the real probability of the system, PI of T. The other is the PIS of T, which is the stationary state, the solution of this equation. So that's the stationary state distribution the system will have if I was to freeze my rates, okay? Now, the stationary distribution can be a non-equilibrium one or an equilibrium one. If the systems fulfill the state balance, then it's an equilibrium one. And here, we can have a mathematical definition of what active heat engine is. So active is typically a word that's not very well defined, right, with an equation. It's almost a synonym to non-equilibrium. But in this case, active here means that if the stationary distribution I would have when I freeze my rates is a non-equilibrium one, then the heat engine is active. If this stationary distribution would be the equilibrium one, then the heat engine is passive, okay? But it's important to remember there are 2 distributions, P, which is the real distribution of the system, and PS, which is the distribution the system would go to if I was to freeze my rates, okay? Okay, so the way you do these things in general is you first start with generalized state balance, which is called the generalized state balance condition. This is not really a condition, it's a postulate in stochastic thermodynamics, but okay, that's beyond the perspective of this talk. But, you know, you write it as an inverse temperature, there is a free energy difference, and then there are the affinities. I hope you are more or less familiar with these terms. But then you can, this one in black is the formula for the entropy, the standard entropy in stochastic thermodynamics. Then you can kind of, if you put these rates in, you can kind of show that the entropy is going to look like that. So the delta S active term is the term associated with the external affinities. That's the one that is going to like grow linearly with the period tau. Then I have the JQ. JQ is QH, okay? In general, it's a more general form of the heat current. But if I'm thinking about the heat engine as the one I showed in the previous figures, that will just be the heat taken from the hot reservoir. And then I have the W term, okay? Now, if you do the same thing with the excess entropy, if you put these rates in, very generally, you can show the excess entropy is going to look like this. There will be an I term, an information theoretic term that I'm going to talk about in the next slide. There will be the JQ term and the W term. And so what is happening here physically is that there is this informational term, and that's the reason why active heat engines can do things that passive heat engines cannot do, okay? What is this I term? Okay, so for that, I have to think about 3 distributions. I told you about P and PS. So P is the real distribution of the system. PS is the stationary distribution the system would have if I was to freeze my rate. And then I have P equilibrium, which is the stationary distribution the system would have if I am to make all these A alphas equal to 0. So if I make all A alphas equal to 0, then my stationary distribution would be the equilibrium one, okay? So I want to talk about three distributions. PS is the real stationary distribution that the system would have, and P equilibrium is the stationary distribution it would have if I was to set all my A alphas equal to 0, okay? All right, so if I can think about ln of PS divided by P equilibrium, and the bracket here mean an average, I can kind of write this as the Kubic library between P and P equilibrium, and the minus the Kubic library between P and PS. Note that if P equilibrium and PS are the same, meaning if I have a passive heat engine, this quantity would be 0, okay? Now I can take a time derivative of this quantity, this information theoretical quantity, which is this Kubic library difference. So there are two Kubic library distances, and I take a time derivative. There will be two contributions. The first contribution is the contribution due to the jumps, and the second contribution is the contribution due to the time dependence of PS and P equilibrium, okay? Now, if I integrate this finger over a period, so if I integrate ddt of ln of PS divided by P equilibrium, the average of that over a period, I'll get 0. The reason I'll get 0 is because this quantity is periodic, right? So if I do the derivative of a periodic quantity and I integrate over one period, I get 0, meaning that the contribution due to the jumps will equal minus the contribution due to the time dependence of the quantity, okay? And now if I just take one of these contributions, either the contribution due to the jumps or the contribution to the time dependence, I will get the I term that shows up in my exercise envelope, okay? So this I term has an information theoretical interpretation as part of the time derivative, either the part due to the jumps or the part due to the time dependence of this difference in Kubic libraries. The important point about the I term is that if the heat engine is passive, meaning PS and P equilibrium are the same, I term becomes 0. If it's not passive, it's an active one, then the I term is non-zero. The physics here, is that in the end, if I have an active heat engine, it does not really matter how much energy my dissipative degrees of freedom are dissipating. The really important thing is how do you shift your distribution? So from P equilibrium to PS, what's the shift you are doing as quantified by this I term? That's the thing that will allow you to do things such as extracting or having an efficiency that goes beyond the kernel efficiency, okay? Or the pseudo efficiency, I should say. So that's the story. Now there's the idea of coarse graining. Coarse graining is very important because, when you think about the experiment, if you try to imagine a sort of active heat engine, probably you'd have to look at some variable X, which in the case of the experiment would be the position of the colloidal particle, and some variable A, which would characterize the dissipative degrees of freedom that you cannot see, which are the bacteria, right? And it turns out that, you can work out these things, you can do the coarse graining. For example, if I look at the variable X, things are non-Markovian now because these capital K rates are actually, you have to know the variable A to determine them. So, if I think about only about X, this would be a non-Markovian dynamics. But, again, if I think about the experiment, X would be the position of the particle, and A would determine the position and maybe something else about the bacteria. A would be something that tells you the state of the bacteria, and X is the position of the particle. This also gives an idea of the generality of our approach. There is no need that your system is Markovian. What you do need is that when you look at the full thing, the full picture of the degrees of freedom that you cannot see, plus the degrees of freedom that you can see, everything together must be Markovian. So I would say this is very general, which should apply to almost anything you can think of in molecular biophysics, for instance. And what will happen when you do the coarse graining is that the structure of the second law will not change, okay? Basically, the physics remains the same. You will have a coarse grained die. The good thing of this is that, if you think about the experiment, I can measure all these things, the I, the JQ, and the W, by only looking at the position of the bacteria. There is no need to know anything about the bacteria. I only have to look at the position of the particle, okay? And, this point that the structure of the second law retains its structure under coarse graining is not really new. The standard second law, it's new for the excess entropy. There is a paper from, I think, 2012, if I'm not wrong, called Stochastic Dynamics under coarse graining by Maximilian Esposito. It's a nice paper, and there you can see that for the standard entropy also, when you do coarse graining, the structure of the second law will not change, okay? We have done also a numerical case study that is very similar to the experiment. So it's a passive particle in a 2D interacting with a bunch of active particles representing the bacteria. And, all these things will work out the same as for the simple models. there is a correct efficiency which also accounts for the I term. Okay, if there is the QH and the I term in this correct efficiency, and this correct efficiency will be bound by the kernel efficiency. This is represented here in this figure, right? The pseudo efficiency goes above the kernel bound, but the correct one will not go above. Okay, so basically what I told you is that the appropriate statement of the second law comes for an active cyclic heat engine, comes from the excess entropy, and when you do that, there will be some informational theoretical term that will emerge. So the amount of energy dissipated does not really matter. What really matters is the informational theoretical term. This work done with Arya Datta, who was my PhD student. He's now in industry, and Patrick Petsonka, who just gave the previous talk. And what we have been working on, you can also do an active refrigerator. I mean, you can find regimes where you can even find a regime where the active system will be engine and refrigerator at the same time. And we also have been working on linear response theory for active heat engines. That's a pretty interesting thing because, you know, the point where the entropy becomes zero, the excess entropy becomes zero, is actually a non-equilibrium steady state. So it's kind of a linear response theory with respect to a point that is like a non-equilibrium steady state. Okay. And we are doing this by doing some sort of fluctuation theorem for the currents for the excess entropy. Okay? It's kind of a long story. It should be out in a couple of months, I guess. And with this, I finish. Thank you for your time.